Chapter 3: Simple Neural Networks. In the previous chapter, we explored machine learning in general and also focused on linear models trained via gradient-based optimization. In this chapter, we move up a notch and consider logistic regression and multinomial softmax regression models used for regression and classification. These models often play a key role in statistical modeling and are also very important from a deep learning perspective. Logistic regression and multinomial regression models are shallow neural networks, but also involve nonlinear activation functions, and hence understanding their structure and means of training is a gateway to understanding general deep learning networks. In exploring logistic and softmax regression, we're introduced to some of the basic mathematical engineering elements of deep learning. These include the sigmoid activation function, the cross-entropy loss, the softmax function, and the convexity properties that these models enjoy. We also use the opportunity to consider simple but non-trivial autoencoders that generalize the PCA method introduced in the previous chapter. In section 3.1, we consider the statistical viewpoint of the logistic regression model. In the process, we see how binary cross-entropy loss results from maximum likelihood estimation. In section 3.2, we consider the same model, only this time as a shallow neural network trained via gradient descent. In section 3.3, we adapt the model to multi-class classification. Here, we introduce a softmax function, as well as a categorical cross-entropy loss. In section 3.4, we investigate feature engineering for such models and see how additional features extend the resulting classifiers to have nonlinear decision boundaries. In section 3.5, we momentarily move on to unsupervised learning and consider simple nonlinear autoencoder models. In that section, we also discuss general autoencoder concepts and describe a few applications of autoencoders. Section 3.1: Logistic Regression in Statistics. Logistic regression can be viewed as the simplest nonlinear neural network model. However, outside of the context of deep learning, logistic regression is a very popular statistical model. In this section, we present logistic regression via a statistical viewpoint. We show how to estimate parameters via maximum likelihood estimation, and in the process are introduced to the binary cross-entropy loss function in deep learning models, including logistic regression, but also beyond. Note that the statistical view of logistic regression also incorporates parameter uncertainty intervals, hypothesis tests, and other statistical inference aspects. Literature for such statistical inference aspects of logistic regression is referred to at the end of the chapter. The model. Logistic regression is a model for predicting the probability that a binary response is 1. It is suitable for classification tasks, a concept described in section 2.2, as well as for prediction of proportions or probabilities. From a statistical perspective, it is defined by assuming that the distribution of the binary response variable, y, given the features x, follows a Bernoulli distribution with success probability phi of x. Let's look at the footnote about a Bernoulli distribution. This is a probability distribution of a random variable having only two outcomes, 0 or 1. It's a special case of the binomial distribution where the parameter for the number of trials is set at 1. That is, if we represent the random variables of the feature vector and the scalar response via x and y respectively, then the probability that y equals 1, given that x equals x, is phi of x. So phi of x is a probability of success. And the probability that y equals 0 is the complement, 1 minus phi of x. To capture the relationship between x and phi of x, the model uses the odds of phi of x, namely phi of x divided by 1 minus phi of x. That's what you call odds, via the log odds represented as the logit function. So the logit function, logit of u, is log of u divided by 1 minus u. Using this notation, the logistic regression models assume a linear, well, affine, relationship between the feature vector x and the log odds of phi of x. Namely, this is the underlying relationship in logistic regression. The logit, or log odds, of phi of x is affine in x. Here, the feature vector x in Rp, the parameter space is theta, which is R times Rp, and the parameters are denoted via theta equals bw. Namely, the number of parameters is d equals p plus 1, similarly to the linear regression models of section 2.3. Like the linear regression model introduced in section 2.3, the scalar parameter b is called the intercept or bias, and the vector parameter w is called the regression parameter or weight vector. The fact that 3.3 presents logit on the left-hand side in contrast to simply the expected response y as one would have in linear regression, such logistic regression is a non-trivial form of a generalized linear model, GLM. We don't discuss GLM further. Nevertheless, it is good to know that using GLM terminology, logit plays a role of a link function. See notes at the end of this chapter for details and references. A closely related function to logit, central to logistic regression and deep learning, is the sigmoid function, also called the logistic function. It is denoted in this book sigma sub sigmoid. That's how we denote this function. And is also discussed in section 5.3. That's in chapter 5, where it's plotted in figure 5.6. Its expression is sigmoid of u is 1 on 1 plus e to the minus u. Let's look quickly at figure 5.6 from that chapter. So figure 5.6 from chapter 5. So here we have u, here on A. We have multiple functions, and we call these functions activation functions, but now we just focus on the sigmoid. So the sigmoid is the green function. So it's monotonically increasing. It's 0, it's a half. At negative infinity, going to negative infinity, it's 0, and going to positive infinity, it's 1. In fact, this sigmoid function, also called a logistic function, is a cumulative distribution function or probability distribution. Back to chapter 3 here. It has domain R, range 0, 1, and is monotonically increasing. Note that the logit function and the sigmoid function are inverses. So here's back, our logit function was back here. So these two guys are the inverses of one another. That is, the sigmoid applied to the logit is like the logit applied to the sigmoid, and they're both just u, which gives us the identity. So they undo each other. Applying sigma sigmoid to the representation model in 3.3, we obtain the common representation of the logistic regression model. So if we go to this relationship and apply sigmoid, so sigmoid will undo the logit, and then we have phi of x, just a phi of x, would be the sigmoid of this thing. Okay, that's what we get, and let's see it. So phi of x which we just remind is the probability of the response being 1, being given the features, x, and the parameters, is sigma sigmoid of this affine relationship, which we can just write like that. Side note, the logistic distribution. When considering the statistical logistic regression model, it is also interesting to represent the relationship between x and y via a continuous latent variable denoted via z. A latent variable is an unobserved quantity. In the case of logistic regression, z allows us to use the linear model representation. Z equals an affine relationship on x plus epsilon with y being 1 if z is greater than 0 or greater or equal to 0, and y being 0 if z is less than 0. Here, the noise component epsilon follows a standard logistic distribution, whose cumulative distribution function, f epsilon u, which is the probability of epsilon being less than u, is actually given by the sigmoid function. So a logistic distribution has cumulative distribution function, which is a sigmoid function. Such a representation agrees with, so if we use this latent variable representation, it agrees with the basic definition, 3.5 up here. Since phi of x is a probability of y being 1 given x, and y is going to be 1 according to this representation if and only if z is greater or equal than 0. Z being greater than or equal than 0 is this expression being greater than or equal than 0. Now we make a transition to this expression where we put a negative here being greater or equal than 0, and we'll explain this step in a second. And once we have this step, then we can just rearrange the bits inside the probability and get that's the probability of epsilon being less than this, and that's a cumulative distribution function of epsilon at this point, which is the sigmoid at this point, at the affine relationship. The one step we need to explain is this step here, and we write this here. Note that in the step between the second line and the third line, we use the fact that the standard logistic distribution of epsilon is symmetric about 0, and hence epsilon and minus epsilon are equal in distribution, and hence we can interchange them inside the probability expression. We do not use a latent representation 3.6, this latent representation, any further. Yet it may be interesting to know that if one chooses to use a Gaussian distribution for epsilon in 3.6, so say we now like this kind of way of representing things, and we say let's not use this as a logistic, but rather as a Gaussian distribution. So if we use a Gaussian distribution for epsilon 3.6 in place of the logistic distribution, the model turns out to be what is called a probit regression model instead of 3.3. And hence it's interesting, and some people in statistics use probit instead of logit. Okay, so that was a side note. Back to our main story. Estimation using the maximum likelihood principle. When statistical assumptions are imposed, maximum likelihood estimation, MLE, is a very common statistical method for estimating parameters. While most deep learning models in this book do not use MLE or other statistical point estimation techniques directly, exploring how MLE works for logistic regression is insightful. Central to MLE is a likelihood function, which we denote here via L, from the parameter space theta to the reals. It is a function of the parameters theta in the parameter space, which is obtained by the probability, or often the probability density, of the data for any given parameter value theta. The idea of MLE, maximum likelihood estimation, is to choose values for theta that maximize the likelihood function. We see this in action for the logistic regression model now. Consider the training observations, D, which are x1, y1 up to xn, yn, denoted in a similar way to the way D is defined for the linear model in section 2.3. Here, each label yj is encoded via either 0 or 1, and the feature vector xj is a p-dimensional vector in Rp. A common assumption in statistics and machine learning is that all feature label pairs xj, yj are identically distributed and mutually independent. That is often denoted IID. With this assumption, we aim to estimate the parameters theta equals b, w. The likelihood function in this IID case is likelihood of theta given the data is the product of the probabilities of y being yi given x equals xi, where L theta d is viewed as a function of theta given the observed sample d. The product is due to the independence assumption arising as part of the IID assumption. In the context of the underlying logistic model, using 3.1 and 3.5, and since the labels are either 0 or 1, the likelihood evaluates as, so let's just remember what 3.1 and 3.5 are. So 3.1 was just the definition of what phi of x is. That's a probability of getting a 1, right? That was 3.1. And 3.5 was the central representation of the logistic regression model. Okay. So that's 3.5. So back to here, using 3.1 and 3.5, and since the label are either 0 and 1, the likelihood evaluates as the product of phi xi to the power yi times 1 minus xi times 1 minus yi, where phi of x is the sigmoid. Now, the reason we get this is, think about that if an observation yi is 0, for example, then this whole thing is 1, and it doesn't count in the product. And then this is 1. We get 1 minus that, and that's a probability of getting 0. Okay. Similarly, if an observation yi is 1, then this is 1, and this is 0, so this whole thing is 1, so this doesn't count. And then we get the probability of getting a 1 every time given the features xi. The maximum likelihood estimate is defined as a value of the parameter theta which maximizes the likelihood function. That is, MLE is a value which maximizes the probability of the observations D, assuming the logistic model. With 3.8 available, one may proceed to optimize the likelihood directly. However, in the case of logistic regression, and in many other cases where MLE is applied to IID data, it is more convenient to maximize the logarithm of the likelihood, called the log likelihood, denoted via little l of theta d, which is just the log of the likelihood. This is equivalent to maximizing the likelihood, since the log function is a monotonic increasing function. For logistic regression, the log likelihood expression, so taking log of this thing, we get this thing because the product becomes a sum, and the powers move over to the side, and that's what happens when we take the log the likelihood. The log likelihood expression is the summation over all observations of yi times log of phi of xi plus 1 minus yi times log of 1 minus phi of xi. And the maximum likelihood estimate, MLE, is represented via the argmax over this thing. Okay, so that's the maximizer of this thing, where theta is an element of R1 times RP. We could have just done R of P plus 1, but we specifically do this because this is for the B and this is for the W. Okay, just a way of writing it. And that also equals the argmin. So if you maximize a function, it's like minimizing its negative. And we might as well also stick this 1 on n. That's for reasons that we'll see shortly. We say this since maximizing L of theta is the same as minimizing negative L of theta, and the positive factor 1 on n does not change the optimization, yet is useful in the presentation that follows. Now, this is important. One can show that the function negative 1 on n L of theta, that's the function that we're minimizing, is convex, and hence a global minimum exists. Aspects of optimization and convexity are also further overviewed in section 4.1. That's in chapter 4. However, in contrast to the linear model, where an explicit analytic solution, as in 216, exists, in the case of logistic regression, there is no analytic solution for the minimizer, and hence optimization algorithms are needed to find the MLE 310. Okay, so we don't have the pseudo-inverse that gives us the solution. The binary cross-entropy loss. We've already claimed throughout chapter 2 that learning almost always involves optimization. The MLE-based paradigm for logistic regression certainly reinforces this claim. We now reposition logistic regression MLE in terms of minimization of a loss function, following similar lines to learning of the linear model of section 2.3. This setup continues straight into more involved deep learning models that follow. Recall the general loss function formulation, which we first presented for linear models in equation 211 in chapter 2, where the loss is C of theta given data, and that's the average over the individual losses CI. In that context of linear models, the individual loss CI theta, and it depends on the label yi and the predicted label y hat I, was the square error. Logistic regression learning follows similar lines, except that CI theta, that's the individual loss for an observation, is not the quadratic loss. To see this, revisit the minimization form of 310 together. So 310 was right here. That was a minimization form of 310. This guy, minimization form of 310. Together with the log likelihood expression 3.9. And 3.9, this is the important expression. Let's even give it a different color here. So that's the log likelihood expression. Okay, so we are minimizing sort of this expression, except for with a -1 on n, but that doesn't matter much. The minus matters a lot. The scaled negative likelihood that needs to be minimized can then be represented as, so we are just rewriting the expression as follows, as put the negative that was before outside inside as the sum of these things, where y hat I is phi of xi, which is the sigmoid of the affine relationship on the features. Okay, so see y hat I here is these Nice. Phi of xi and phi of xi inside here. This then implies that for logistic regression, the loss for each data sample is Ci, which is this thing which we call Ce underscore binary, and that's the binary cross entropy loss of yi and yi hat, where Ce binary of the y and the y hat is this expression, negative of y log y hat plus 1 minus y times log of 1 minus y hat. And that's called the binary cross entropy estimate applied to observation y and prediction y hat. So basically what we've seen is that the loss, the minimization, well, the maximization, maximum likelihood, if we reposition it as a minimization, then what we are minimizing is a binary cross entropy loss, which falls in the same paradigm as the previous chapter and will continue throughout this book, where this is the type of loss that we have, and the individual loss for an observation is a binary cross entropy loss. In the process, we define this function, which we call the binary cross entropy, Ce binary. In general, the phrase cross entropy, and specifically entropy, is rooted in information theory. Appendix B outlines relationships between cross entropy and related to terms in information theory. However, these relationships are not critical for understanding of deep learning. In terms of relating 311 to the probabilistic meaning of cross entropy, so 311 to the probabilistic meaning of cross entropy, see first the definition of cross entropy for two probability distributions in B1, and then see the specialization to distributions with binary outcomes in Appendix B4. So we won't do this now, but when we revisit the appendix in this video series, we'll reconnect it to this. Okay, so that's appendix. We also mentioned that while we arrive to the binary cross entropy as a byproduct of maximum likelihood estimation for logistic regression, in general, binary cross entropy has become the default loss function for more complex binary classification deep learning models, as surveyed in chapter 5 onwards. So in logistic regression, if you accept maximum likelihood for logistic regression, you get binary cross entropy immediately by default. But other deep learning models that don't have maximum likelihood interpretation, one still uses often, if it's binary classification, you still use a binary cross entropy. Okay. Predicted probabilities and parameter interpretability. For any observed or postulated feature vector, X star and RP, the output of logistic regression is Y hat, which is phi of X star. This is a probability. It's a number between 0 and 1, which can be interpreted as in the left-hand side of equation 3.1. So the probability of getting 1 given the features. Hence, at its core, the logistic regression model 3.5, the main model, yields probabilities as outputs. Below, we see how these probabilities can be used for classification. Yet, first, let us consider prediction of probabilities or proportions. Recall the breast cancer example presented in section 2.2, that's in the previous chapter, where we overviewed concepts of binary classification. In that example, based on the Wisconsin breast cancer dataset, we used a training set to create two logistic regression models. The first model used the smoothness worst feature as a single coordinate of X. And the second model used all possible 30 features. We now continue to use this data set, this time using all n equals 569 observations for statistical inference, and setting a so we're not breaking it into a train and a test, and setting a single feature model based on the area mean feature, and a two-feature model based on area mean and texture mean. With the estimated two-feature model based on estimated parameters theta hat, which is B hat, W1 hat, W2 hat, the predicted probability for an observation X star is the sigmoid applied to the intercept plus W1 hat times X star area mean, W2 hat times X star texture mean. Okay, so instead of using indices here, we're actually naming these features. Where for clarity, we subscript the coordinates of the feature vectors X star with a feature name, just like I said. Using 3.3, this can also be represented as, so now if we just take logit on that, then that's log odds of y hat is affine in these features. Okay, that's what we see here. The representation in 313 is appealing since it endows the estimated parameters B hat, W1 hat, and W2 hat with a concrete interpretation. First, observe that the log odds is linearly described by the features area mean and texture mean. This means that it is estimated that a unit increase in area mean will see the log odds increase by W1 hat. A unit increase in texture mean will see the log odds increase by W2 hat. And similarly, when both features are set to 0, the log odds is at the value B hat. This interpretation of parameters is clearly not limited to a model with two features, as it would work for any number of features. In practice, it is more convenient to interpret the odds given by, so apply now an exponent to both sides of the equation, and you get the following by this representation. So not the log odds, but just the odds is the exponent of B of this affine expression. Okay. Specifically, an increase of area mean by 1 unit implies a multiplicative increase for the odds by a factor of EW1. And similarly for texture mean by a factor of EW2 with hats on the W's. With this view, it is typically common to consider the odds ratio, where the meaning of the multiplicative factor EWI hat is the ratio between the odds of a model where the feature is at some level xi between the odds at some level xi plus 1. This is especially useful where features are binary, but also in general. Further note that when EWI is greater than 1, we say the feature has an increasing effect on the probability of the outcome being positive, and in the opposite direction, a feature with EWI hat less than 1 yields a decrease in the probability when the feature is increased. Such parameter interpretation transcends from linear models to logistic regression models, as well as to other statistical models. This interpretability property often makes models extremely attractive in biostatistics and similar fields. It means that estimated parameters of the model are not only useful for their predictive ability, but also for reasoning about the relationships between variables. As we progress beyond this chapter to more complicated deep neural networks, direct interpretability of parameter values is often lost. In such non-interpretable cases, the parameter estimate theta hat is not a useful learning outcome on its own, but is rather only useful for the tasks of the model. Nevertheless, we mentioned that an active area of machine learning and deep learning research is to seek interpretable models. In figure 3.1, we present the actual fit of the single feature model and the two feature model for the Wisconsin breast cancer observations. The response y hat is a probability of malignant lumps, whereas the data involves observations with y equals 1, that's positive, i.e. malignant, and y equals 0, that's negative, i.e. benign. In A, we see the sigmoid function applied to the affine relationship beta hat plus W1 hat x1 for the estimated single feature model directly, and also plot all the observation with a slightly random jitter on the y-axis so that they can be visualized easily. Where we cut off high outliers. So let's first look at A. So here are the observations. This is only your single feature, x1. Y hat, the observed responses are either positive or negative. Okay. And we just plot them with a bit of jitter so it'll be visible. And this is a fitted model. Okay. In B, the sigmoid function is applied to this affine function with two inputs, x1 and x2, yielding a surface where we omit plotting the actual observations because it would be too messy. In both the univariate and multivariate cases, it is evident that models present monotonic relationships between each of the variables and the predicted probability. This property holds for any number of features. So here you've got your two features, and you've got your surface, your sigmoidal surface. And in A, we also do a confidence band, which is a byproduct of the model, but we don't discuss this further in this book. Logistic regression for classification is a linear classifier. In addition to the application of probability prediction as described above, logistic regression models can also be naturally used for binary classification. We've already seen how to convert such models into binary classifiers. This was first seen in section 2.2 in the previous chapter, where we introduced the threshold-based classifier in equation 2.5 of that chapter. With the label prediction big Y hat set to 1 positive if Y little if the actual probability value or model output value is greater than tau, and 0 negative otherwise. So you have some threshold tau. As an illustration, consider the two features breast cancer prediction model with a response surface as in figure 3.1b. So this response surface, let's see it again, it's figure 3.1b. By setting tau equaling half, for this model, we get a classifier as illustrated in figure 3.2. So let's first look at figure 3.2. That's figure 3.2. So here now we set tau equals half, and we're looking at the two features, x1 and x2. And when tau equals half, we get this threshold. Okay, so all of the points to the left of the threshold have this surface here, less than half. And all of the points to the right of the threshold on the x1, x2 plane are greater than half. Okay, that's what happens there. The red region corresponds to potential feature vectors that would be classified as negative, benign. Okay, so the red is negative. Let's see it, benign. Okay, that's for y equals 0. Sorry, so that's a region for benign. And the blue region corresponds to positive, which is malignant. It is seen that many, but not all of the training samples are correctly classified. So when you look at the actual data samples, look at the red mostly, or a lot of them fall in the red region, and the blue, a lot of them fall in the blue region. Interestingly, the classification boundary appears like a straight line, or more precisely, a hyperplane in the feature space. One may then wonder if this is a property of logistic regression. We now show that, in fact, logistic regression-based binary classifiers are linear classifiers. Such linear classifiers separate the feature space via a single hyperplane, big H of x, which is B plus W transpose X, where B is a real valued and W is again p-dimensional, are the parameters of the hyperplane. Since every hyperplane cuts Euclidean space into two half spaces, a natural way to use a hyperplane for classification of a feature vector is y hat, big, is negative if the hyperplane is negative, if the point of the hyperplane is negative, and positive if the point in the hyperplane is positive. This means that if x star falls in one half space, the classification is negative, and in the other, it is positive. The distinction on the boundary is arbitrary. To see that logistic regression is a linear classifier, consider the estimated model parameters theta hat equals b hat comma w hat, and the probability prediction y hat. The positive classification then occurs if y hat is greater than tau, i.e. if the sigmoid of this affine combination is greater than tau. We can then apply the logit function 3,2 to this inequality to undo, because it's the inverse of the sigmoid. Since Logistic's monotonic increasing function is an inverse of the singular function, we obtain this type of thing. Or if we rearrange, now we open up the, we just rearrange things inside the log, we get this type of thing. We thus see that the hyperplane parameters, because now it's written in the form of the hyperplane parameters, we now see that the hyperplane parameters associated with the logistic regression classification are, this is your intercept for the hyperplane, and this, let's paint it in yellow, is your slope for the hyperplane. Okay. This shows that logistic regression with a threshold rule yields a linear classifier. Note, in fact, that with the same argument, any model of the form y hat, so any model of the form y hat is some sigma of some affine function, where sigma is some bijection, some invertible function from R to R, so the sigmoid was invertible, yields a linear classifier. This naturally includes the linear model-based binary classification outlined in section 2.3, because then that sigma was just identity function. It includes the probit model mentioned earlier in this section, even though we didn't dive into it. It also includes any shallow neural network for binary classification that has strictly monotonic activation function, a concept introduced in the next section. We'll see what an activation function is then. Other very common linear classifiers not surveyed in this book is a class of support vector machines. They're linear classifiers, but they're completely different. Note that one often transforms classifiers with linear decision boundaries into more expressive classifiers via feature engineering. In section 3.4, we explore how feature engineering-based transformations of the features may yield non-linear decision boundaries for the models studied in this chapter. Okay, so this concludes section 3.1. As always, we hope you enjoyed, learned something, and let us know what you think in the comments below. Thank you.